Hi children, welcome to another chemistry class. See, in this session, we are going to discuss a review on the chapter Chemical Kinetics. That is the fourth chapter from the second year topic of chemistry. Can we start? Ready? Yes. All of you know Chemical Kinetics. The chapter is dealing with the rate of reaction. In the chapter Thermodynamics, we are dealing with the energy changes. What is enthalpy changes, internal energy changes, spontaneous nature of the reaction, whether the reaction is spontaneous or not, like that. Thermodynamic feasibility of the reaction. While there is another form of handling the chemical reactions, which is kinetic nature of chemical reactions. Kinetic nature of chemical reactions. Got it? So the chapter is dealing with the rate of reactions, right? Basically, there are three types of reaction. All of you know. Number one, extremely slow reaction. Extremely slow reaction. The measurement of kinetics is not practically not that much easy because it is too slow, immeasurable. It is too slow to be measured, like rusting of iron, right? And the second one is moderately slow or moderately fast. Moderately slow or moderately fast, we can say. That is the kind of reaction we are dealing in the chapter basically. And the third one is extremely fast reaction. Extremely fast reaction, violent reactions. That too is too fast to be measured. Of course, we have modern methodologies for finding the kinetics called photolysis, etc., flash photolysis, etc. But still, our point of discussion in the chapter is mainly dealing with the moderately fast reaction or so-called moderately slow reaction. Right, in the syllabus content. There are other types of reactions like reversible characters, parallel reactions, consecutive reactions, enzymatic mechanisms, which are dealing with the complex chemistry of kinetics, which we are not actually involving in the concerned chapter. In the chapter, we are dealing with the important ideas regarding moderately slow reaction, that too simple kinetics reaction we are dealing with. Right? So first of all, what is meant by rate of the reaction? All of you know what is meant by rate of the reaction. Rate of the reaction, R is equal to change in concentration. Change in concentration of reactant or product divided by time taken. That is the rate of the reaction. Change in concentration of either reactant or product divided by time taken. So we can write it as delta X by delta T, or you can write it as minus delta R by delta T, or it is plus delta P by delta T. A minus given to in case of reactants because reactant concentration decreases with the time, and plus given to product because product concentration increases with the time. So rate of reaction can be represented as delta X by delta T. Delta X means a change in concentration. Delta T is time taken. So this will be minus delta R by delta T, that is decrease in concentration of reactant by time taken, and plus delta P by delta T, that is increase in concentration of product by time taken. Right? What is the unit of rate? What is the unit of rate? Yes, it is concentration time inverse. Concentration time inverse. Concentration is molarity. Molarity second inverse, or it is mole per liter per second. That is the unit of rate of reaction. In case of gaseous reaction, instead of concentration, we take pressure. We take pressure, that is say atm per second, or it may be bar per second, like that. It can be in case of gaseous reactions. Is it clear? Is it clear? That is about the rate of reaction. So rate of reaction will be change in concentration divided by time taken. So for a hypothetical reaction, say A plus B giving C plus D, 1 mole each, you can write R is equal to minus delta A by delta T equal to minus delta B by delta T equal to plus delta C by delta T equal to plus delta D by delta T. In case of reactants, we give the sign minus. In case of products, we give the sign plus. Right? It can be represented in terms of change in concentration of any one of the reactant or products. It can be written in terms of A, it can be written in terms of B, it can be written in terms of C or D. In case of A and B, there will be decrease in concentration indicated by minus. In case of C and D, there will be increase in concentration designated by plus. Okay. And how do we represent graphically? How do we represent graphically reactant converted to product? Graphically, concentration of reactant along the y-axis and time taken along the x-axis. And suppose the variation comes out like this, how do we find the rate? It's very simple. Time t1, concentration R1, time t2, concentration R2. It will be rate is equal to R2 minus R1 divided by T2 minus T1. Quite simple to understand. R2 minus R1 will be negative because it is decreasing. So it is minus delta R by delta T, like that. And this is called the average rate of the reaction. Average rate of the reaction. How do you represent in terms of products? How do you represent in terms of products? Very simple, no? Concentration of products along the y-axis and time taken along the x-axis. The graph will be somewhat like this. This is product concentration increasing. So how do you find the rate? At the time t1, concentration of product P1, at the time T2, concentration of product P2. Therefore, R is equal to P2 minus P1 by T2 minus T1. No doubt, it will be P2 greater value minus lower value. It will be plus. So it is plus delta P by delta T. And this is called the average rate of the reaction. That means rate observed over a considerable time period. Rate observed over a considerable time period. Is it clear? So what we have written here is average rate. Average rate. Suppose we consider the time period is too small. That means delta T tends to 0. Suppose delta T tends to 0, then it is called the instantaneous rate. Suppose this delta T tends to 0, just imagine this is delta T. Imagine delta T tends to 0. It seems like a instant. It seems like a instant, and then we write R is equal to delta X by delta T. When delta T tends to 0, we write it as dx by dt. That is the differential form of rate of reaction and is called the instantaneous rate. Rate observed at a particular instant. How do you do that? Very simple now. We take concentration of reactant along the y-axis and time taken along the x-axis. If you get a graph like this, at a particular time, how do you find the rate? At a particular time, how do you find the rate? It is observed by a tangent plot at that point. We plot a tangent at that point, and the slope of the tangent will be equal to rate of the reaction, and that is called the instantaneous rate. How do you represent mathematically? R is equal to delta x by delta t becomes dx by dt, where dt is a very small time interval. Imagine dt, a very small time interval such that it looks like an instant. This is dt and this is dr. So it is going to be minus dr by dt. And it looks like an instant. It looks like an instant. So delta t tends to 0 means t1, t2 coming very close such that it looks like an instant. That is called the instantaneous rate. And that will be represented in terms of differential form of rate of reaction. So how do you write the rate of reaction in differential form? For the hypothetical reaction given A plus B giving C plus D, R is equal to minus dA by dt equal to minus dB by dt equal to plus dC by dt equal to plus dd by dt, like that. That is differential form of rate of reaction. Now how comes if it is, this is 1 mole A plus B giving C plus D, 1 mole A, 1 mole B, 1 mole C, 1 mole D. Suppose it is a given actual coefficient stoichiometry like A moles of A reacting with the B moles of B giving C moles of C and D moles of D. A typical hypothetical equation given. How do we write the differential form of rate of reaction? All of you know that. I am reminding you only. So it is R is equal to minus dA by dt into 1 by A equal to minus dB by dt into 1 by B equal to plus dC by dt into 1 by C equal to plus dd by dt into 1 by D. That is the differential form of rate of reaction for the hypothetical equation A moles of A plus B moles of B giving C moles of C plus D moles of D. The coefficients will be written 1 by A, 1 by B, like that. And understand, rate of reaction you can express as this data, rate of reaction. In terms of A, B, C, D, you can do that like that. While this particular data can be called as decrease, that is the rate of disappearance of A. dA by dt, that is called the rate of disappearance of A. This is called the rate of disappearance of B. And this is called the rate of formation of C. And this is called the rate of formation of D. Remember what I have highlighted now. That is rate of formation of D, while this is rate of reaction. The entire terminology will be rate of reaction. What I have highlighted is rate of formation of C. If you take including 1 by C, that is rate of reaction. So rate of reaction will be including 1 by A, and this highlighted term will be rate of disappearance of A. This is rate of disappearance of B, and including 1 by B, this is rate of reaction, like that. Please keep it in mind very clearly. So minus dA by dt, that is called the rate of disappearance of A. Minus represent disappearance. With the stoichiometry 1 by A, that is rate of reaction. Is it clear? Fine. So that is the differential form of rate of reaction. For example, if you take any stoichiometry, say N2 plus 3H2 giving 2NH3, the rate of reaction will be represented as minus dN2 by dt equal to minus dH2 by dt into 1 by 3 equal to plus dNH3 by dt into 1 by 2. Right? So what do we understand? The rate of reaction is equal to the rate of disappearance of nitrogen. Rate of reaction is equal to rate of disappearance of nitrogen. While while the rate of disappearance of hydrogen will be 3 times the rate of the reaction. See, 3 mole hydrogen is disappearing. The rate of disappearance of hydrogen, this term will be 3 will come here. 3 times rate of reaction. Like that. And what about rate of formation of ammonia? Rate of formation of ammonia will be 2 times the rate of disappearance of nitrogen. When 1 mole nitrogen disappear, 2 mole ammonia is forming. Rate of formation of ammonia will be 2 times the rate of the reaction, 2 times the rate of disappearance of nitrogen. And the rate of disappearance of hydrogen will be 3 times the rate of disappearance of nitrogen. Like that. That is the logic of writing this formula. I hope it is pretty clear and revised. Right? Next topic is, as all of you know, rate law or rate equation. That is the next topic. Rate law or rate equation. Rate law or rate equation. What is rate law or rate equation? For a reaction, A moles of A plus B moles of B giving products, rate law says that R is proportional to concentration of A to the power X, concentration of B to the power Y. This is rate law. Rate of a reaction is directly proportional to molar concentration of the reactants with a suitable power X and Y. Now, this X may or may not be equal to may or may not be equal to A. Similarly, Y may or may not be equal to B. The coefficients A and B can be equal to or not equal to the power X and Y. For elementary reactions, many times it can be equal, but not necessarily. That is an experimentally determined term. The term X and Y are called the order of the reaction. X is called the order of the reaction. Order of reaction with respect to A. And Y is called the order of reaction. Order of reaction with respect to B. And the sum of X and Y equal to N called the overall order of reaction. Overall order of reaction. And you can write R equal to a constant K into A raised to X. A raised to X into B raised to Y. X plus Y is called the overall order of the reaction, and the constant K is called the rate constant or velocity constant. And this formula is called the rate law or rate equation. Rate law tell us what will be the change in rate of the reaction upon change in concentration of reactants. That is the importance of rate law. So what is rate law? R is equal to, for a typical hypothetical reaction given, R is equal to K A raised to X B raised to Y. This X and A can be equal or can be different. Y and B can be equal and can be different. X and Y are experimentally determined. X is called the order of the reaction with respect to A, and Y is called the order of the reaction with respect to B. The sum of X and Y is called the overall order of the reaction. Right? And what is the significance of this equation? This equation tells us what will be the change in rate of the reaction upon changing the concentration A and B. And it is experimentally determined. Rate law is determined experimentally. Simply looking at the formula given, you can predict rate law. Rate law has to be experimentally determined. Imagine for a particular reaction, just an example I am telling you. Imagine a particular reaction, A plus B giving C is experimentally conducted in a laboratory, and you got R is equal to K A square into B. This is what you are experimentally getting from the laboratory. That means it is found to be a second order reaction with respect to A and first order reaction with respect to B, and overall order of the reaction is 3. So it is x equal to 2, y equal to 1 and n equal to 3. Overall order is 3, x equal to 2, y equal to 1. This is telling us something important points. What is that? A change in concentration of A and B, how is going to influence the rate of the reaction? Imagine A quantity is doubled, what will happen? Imagine A quantity is doubled, what will be reflecting on rate? When this is doubled, what will happen to rate? Very simple to understand. When this is doubled, you get 2 raised to 2 and the consequence on rate will be, it is 4 times. Rate will become 4 times upon doubling the quantity of A alone. Because A quantity when doubled, it becomes A square becomes 2A the whole square. 2A the whole square means it is 4 times. What about doubling the quantity of B? What will be doubling the quantity of B? What will be the consequence? Upon doubling the quantity of B, it will be 2 raised to 1 and the effect will be 2 times. So doubling quantity of A, rate becomes 4 times. Doubling quantity of B, rate becomes 2 times. What happens if A and B both doubled? It will be 8 times. A doubling, consequence will be 4 times. B doubling, consequence will be 2 times. Both A and B doubled. What is the consequence? It will be 8 times. What if both A and B made half? 1 by 8 times. What about both A and B made 10 times? It will be 10 square 100 into 10. It will be 1000 times. What if both are made 5 times? It will be 5 square 25 and 5 raised to 1 5. 25 into 5, 125 times. What if A doubled, B made half? What if A doubled, B made half? When A doubled, effect will be 4 times. When B made half means it is half raised to 1 and the consequence will be half. So A doubled, the effect will be 4 times. B doubled, effect will be half. So it is 4 into half, it will be 2 times. Like that. So rate law clearly tells us how the rate of the reaction changes upon changing the concentration of reactants. That is the importance, and remember, rate law is determined experimentally. By actually conducting the reaction in the laboratory, we find out the rate law and hence order. Remember, order can be 0. Order value can be 0. We call it as 0 order reaction. Order can be 1. Order can be 2. Order can be 3. Order can be remotely 4. Order can be fractional. Order can be fractional. Order can be at times negative. There are 0 order reaction, there are first order reaction, there are second order reaction, there are third order reaction, rarely there are fourth order reaction, there are fractional order reaction, there are sometimes the order can be represented in some cases as negative. These are the characteristics of order of reaction. What is meant by a 0 order reaction? For example, if you conduct the decomposition of ammonia, 2 ammonia on the platinum surface or iron surface, it is decomposing to N2 plus 3H2. If you write the reaction, all of you know, it may be written as R is equal to K into ammonia quantity square if we are considering the stoichiometry. But actually it is not square, it is 0. It is a 0 order kinetics under working conditions of reasonably good pressure. It is a 0 order reaction. That means you get R is equal to K. That means rate will be constant. Rate will be constant for a 0 order reaction. A change in concentration of reactant does not influence the rate of the reaction. That is a 0 order kinetics. Many decompositions like decomposition of ammonia on catalytic surface, decomposition of phosphine on catalytic surface at a reasonably good pressure, photochemical reactions, these are all zero order kinetics. And you need to go through various examples quoted in the materials and the textbook, examples for various types of ordered reactions. For example, all radioactive disintegration reactions are first order kinetics. Decomposition of N2O5, normally first order kinetics. All radioactive decay reactions, it is first order kinetics, like that. Okay. Example for fractional order, you need to keep it in mind from the examples quoted in the textbook and materials. There can be direct questions like that. That is about order of the reaction. Order can be 0, order can be 1, 2, 3, 4, fractional, sometimes negative, etc. There is a similar term, all of you remember, I believe, molecularity. What is meant by molecularity? Molecularity. Molecularity means number of molecules actively involved in a chemical reaction, in the rate determining step of the reaction. Number of molecules actively involved in the elementary step is called molecularity. Molecularity means number of molecules actively involved. Molecularity cannot be 0. Many times the value of molecularity and order can come same, but conceptually they are different. Hope you get the point. Molecularity, order can be 0. Molecularity cannot be 0. Many times order and molecularity value can come same, but they are conceptually they are different. Order can be 0, molecularity cannot be 0. Order can be fractional, molecularity cannot be fractional. Molecularity will be 1, 2, 3 like that. Unimolecular reaction, bimolecular reaction, termolecular reaction, etc. So this is a unimolecular reaction, A converted to product, while this is a bimolecular reaction, and this is also a bimolecular reaction, while this is a termolecular reaction, or this is a termolecular reaction, or this is a termolecular reaction. So unimolecular, bimolecular, termolecular, etc. Polymolecular reactions are of rare probability. So that is the difference between molecularity and order. Order is a value which tells us what will be the change in rate of the reaction upon changing the concentration of reactant. That is order. It is power assigned in rate law. It is experimentally determined, while molecularity is a theoretical value. Many times order and molecularity value can come same, but they are actually different. Order can be 0, molecularity cannot be 0. Order can be fractional, molecularity cannot be fractional. Like that. Okay. Now there is a talk on unit of K, unit of rate constant K. Unit of rate constant K. All of you know R is equal to K into concentration raised to N. So what is K? K is equal to R by concentration raised to N. What is the unit of R? It is mole per liter per second. What is in the denominator? It is concentration, mole per liter raised to N. So what is the general formula for unit of K? So this is mole per liter per second. This is mole per liter raised to N. So what will be the value? Mole raised to 1 by liter raised to N. It will be mole raised to 1 minus N. Liter raised to minus 1, liter raised to minus N. So it will be liter raised to N minus 1 and second inverse. This is the unit of, general unit of K. And the K unit quite obviously depends on order. Suppose order is 0. It will be mole raised to 1 minus 0, liter raised to 0 minus 1 per second, and the unit of K will be mole per liter per second. That is the unit of R itself. What if it is a first order reaction? 1 minus 1 per second. It will be second inverse. What will be if it is a second order reaction? 1 minus 2. So it is minus 1. Mole raised to minus 1. 2 minus 1. So it will be liter, second inverse. What if it is a third order reaction? 1 minus 3. That is mole raised to minus 2. Liter square per second. So that way, the K unit will keep on varying upon up to the conditions of order. When the order value changes, unit of K changes. Unit of K depends on order of the reaction. I think it is clear. Sometimes, giving the unit of K, you may be asked to predict the order of the reaction. Right? Sometimes there may be a question numerical involving in that way also. Now, another next topic, important topic is pseudo order reaction. Pseudo order reaction. What is meant by a pseudo order reaction? Pseudo means false order reaction. There are certain reaction which seems to be higher order, but actually it is following a lower order kinetics. It follows a lower order kinetics. For example, suppose we take A plus 2B giving product, and imagine originally the order with respect to this is 1 and order with respect to this is 2. Just imagine. Therefore, R is equal to, imagine experimentally determine, R is equal to K A raised to 1 B square. Imagine this is the kinetics of the reaction originally. First order kinetics with respect to A and second order kinetics with respect to B. Suppose this reaction is conducted in such a way that B taken is large excess quantity. Suppose it is large excess amount of B taken. You can see the influence of change in concentration of B over the rate of the reaction is eliminated and it becomes R is equal to Ka. Now it is acting as a first order kinetics and we call it as pseudo first order reaction, pseudo unimolecular reaction. For example, acid catalyzed ester hydrolysis. Acid catalyzed ester hydrolysis RCOOR dash plus H2O in acid medium, say X times. You are getting RCOOH and R dash OH. Imagine we conduct this reaction. It is basically R is equal to K into RCOOR dash into H3O plus raised to X. This is the actual kinetics. But most of the time we can see the acidulated water will be large excess quantity. You see the acid water is available in large excess quantity. This is available in large excess amount, large amount. Now what happens is this influence will be cancelled and it becomes K into concentration of RCOOR dash alone. And now it acts as a pseudo first order reaction. Why? Because a change in concentration of ester alone can influence the rate of the reaction. Imagine you are adding ester drop by drop. Imagine you are adding ester drop by drop, 1 drop, 2 drop, 10 drops. When the quantity of ester increases, rate of the reaction increases. Imagine you are adding some water. Imagine you are adding some water. Will it affect the rate of the reaction? No, because already the water is available in excess quantity. So adding more and more acid water is not going to increase the rate of the reaction. If you want to increase the rate of the reaction, you have to add more and more ester, because that is a limiting quantity. Adding more and more water is not going to make any sense. You add more and more ester. then the rate of the reaction will be increased. So the rate of the reaction is influenced by the quantity of ester that is added, not the quantity of that component which is already available, large excess quantity. Such reactions or conditions we call it as pseudokinetics. I hope it is clear. Right? This is an important area. This is an important area from the, important part which we have seen in the chapter. Which all points we have commented so far? Rate of the reaction, average rate, instantaneous rate, differential form of rate of reaction, rate of appearance, rate of disappearance, rate of formation, rate law, rate equation, order, molecularity, characteristics of order versus molecularity, characteristics of rate law, rate equation, unit of K, pseudokinetics. Is it clear? Our next topic in the chapter is determination of kinetics. Determination of kinetics. What are the different methods involved in the determination of kinetics? Determination of kinetics. There are several ways for the determination of kinetics, right? Number one, it is called a graphical method. Number one, it is called a graphical method. Graphical method. Determination of kinetics. Graphical method. What is graphical method? It is adopted for such a reaction. Say A converted to product, where there is only one reactant. Where there is only one reactant, like a decomposition reaction, we can apply graphical method. How do we apply graphical method? We conduct the reaction in the laboratory. We conduct the reaction in the laboratory. Say we are conducting experiment, say number one, it is versus time versus concentration of A. So time 0, concentration of A noted. Time 5 minutes, concentration of A noted. Time 10 minutes, concentration of A noted. We started the reaction proceeding. Like that, we find out at a periodic interval, we find out the concentration of A. So with the time, we find a change in concentration of A. This is what we do in the laboratory. And now the experiment is over. How do you determine the order of the reaction? It is a trial and error technique. First of all, we will be finding the rate of the reaction. How to find the rate of the reaction? Very simple. It is, see, concentration change available, time available. R2 minus R1 by T2 minus T1. You can find the rate. So when the change in concentration and time is available, you can find the rate. So plot rate. Imagine you are getting a constant rate. Then you can conclude it is a zero order kinetics. If you are getting a constant rate, you can conclude it is a zero order reaction. Is it clear? Suppose it is not a constant rate. If it is not a constant rate, you can go for plotting graph. How? Rate, that is the data along this column, versus rate versus concentration. Rate versus concentration you take. This versus this data you take. If you are going to get a straight line graph, you can comment R proportional to A raised to 1, that is order equal to 1. It's as simple as that. So plotting a graph, taking rate versus concentration, if you get a straight line graph, you can confirm it is a first order kinetics. Otherwise, you have to go for finding the next possibility. How to go for the next possibility? You take the square of concentration. Take the square of concentration and tabulate. Now draw the graph again. Rate along the y-axis and concentration of A square along the x-axis. Now if you get a straight line, you can confirm R proportional to A square, that is order equal to 2. second order kinetics. So this is basically trial and error. If you get a constant rate, it is zero order kinetics. If it is rate versus this straight line, first order kinetics. If it is rate versus this straight line, second order kinetics. Or if you are not getting there, go for a third order, try for a third order, fourth order, fractional order. It is trial and error technique. Do until you get a straight line. Right? So the graph that's going to get finally should be like R versus concentration. It should be R versus concentration raised to N. You should get a straight line. R versus concentration raised to N, you should, till this you must try. Till A raised to N, where you get a straight line, you must try. That's a trial and error technique for finding the order of the reaction graphically. Right? So that is graphical method determination of kinetics. This has got limitation that it is used for finding the order of a reaction where only one reactant is involved. Right? Suppose there are two reactants are involved. We can apply another method, that is initial rate method. Initial rate method or Ostwald isolation method. Initial rate method or Ostwald isolation method. Imagine you have reactant A, sorry, A plus B giving product. Imagine the reaction. It is concentration of A taken, concentration of B taken, and the rate is observed. Concentration of A 0.1 molar, B 0.1 molar, and the rate 2 into 10 power minus 2 mole per liter per second. Just imagine. Now, keeping the concentration of B constant, I am changing the concentration of A. Concentration of B remain same. Right? And the new rate observed. New rate observed, it is 10 raised to minus 2. Now, keeping the concentration of A fixed. Concentration of A fixed. I am changing the concentration of B. I am changing the concentration of B. I find that the new order is like this. Imagine this is a data which I am getting from the laboratory. Of course, you need to go to the laboratory and experiment. If this is the data we got from laboratory and is presented in front of us as a numerical problem and ask you to determine what is the kinetics of the reaction, how do you do? You see that A concentration 0.1, 0.2, 0.2, B concentration 0.1, 0.1, 0.2, and the rate observed is like this. You can easily find the order of the reaction. You can easily find the order of the reaction. R is equal to concentration K into concentration A raised to X, B raised to Y. So first formula, R is equal to, first data, 2 into 10 power minus 2 equal to K into 0.1 raised to X, 0.1 raised to Y. Second data, 4 into 10 power minus 2 equal to K into 0.2 raised to X, 0.1 raised to Y. Imagine you are taking the ratio of the two data, means data this and this. You can see this is cancelling and this is 1 by 2. This will cancel, this will cancel. You get 0.1 by 0.2 whole raised to X. So you get 1 by 2 is equal to 0.1 by 0.2 whole raised to X means 1 by 2 whole raised to X. Therefore, X equal to 1. Actually, you don't have to work out anything. You see that when concentration of A is doubled, no change in B. When A is doubled, rate becomes doubled. So the power will be raised to 1. When quantity of A doubled, rate becomes doubled. That means the power of A will be 1. Like that. Now, you can manipulate between data 2 and 3. How is that? 4 into 10 power minus 2 equal to k into 0.2 raised to x, 0.1 raised to y. And now 16 into 10 power minus 2 is equal to k into 0.2 raised to x and 0.2 raised to y. Now see what happens. This gone, and you get 1 by 4, k out, this is out, 0.1, 0.2 raised to, you are taking the ratio, imagine. So it will be 1 by 4 is equal to 0.1 by 0.2 raised to y. That is 1 by 2 whole raised to y. That means y equal to 2. And you are getting the relationship finally, r is equal to k into a into b square. Like that we can determine the order of the reaction. Is it clear? This way we can determine the order of the reaction. I hope it is pretty clear. Right? So graphical method, initial rate method. So next is integrated equations. See, we need to learn integrated equation for two reactions. One is zero order reactions. That is n equal to 0. Let's see the integrated equations, how to understand for a zero order reaction. You know, rate of the reaction R is equal to change in concentration by time, and that is equal to k into r raised to n, and that becomes k into r raised to 0. Since we are dealing with a zero order reaction, that is equal to k. So we get dx by dt equal to k, that is dx equal to kt, and now integrating on both sides, integral dx is equal to k integral dt. All of you know the result. It is x equal to kt, x equal to kt plus c. Right? What is x? What is x? X means amount of reactant converted to product by time t. X means amount of reactant converted to product by time t, right? And that is x is equal to initial concentration minus concentration available at a time t. R0 means initial quantity. R means quantity of reactant available at a time t. So initial quantity minus the quantity available at the time. It will be quantity converted to the product. So x is equal to kt plus c, and you know c means constant of integration. To find the constant of integration, you can apply time t equal to 0. At time t equal to 0, x equal to 0, because x means amount of reactant converted. At a time 0, x will be 0, right? And you get therefore c equal to 0. At one condition, when c is equal to 0, at all conditions c will be 0. So we can write x equal to kt. This is the integrated equation for first order kinetics. And now substituting, you get r naught minus r equal to kt. R naught minus r equal to kt. You can plot a graph taking r naught minus r along the y-axis and t along the x-axis. You will get a straight line like this. Slope of the line is equal to k, right? And even you can rearrange the formula. R is equal to r naught minus kt. Just rearranged. Now you can draw another graph taking r along the y-axis and t along the x-axis. The graph will be like this, where the slope of the graph will be negative minus k, and y-intercept will be r naught. Y-intercept will be r naught. That is initial quantity. So there is a lot of graphs involved in the chapter, and this is the integrated kinetics for zero order reaction. X is equal to KT, or you can write K is equal to R naught minus R by T. Several form you can write, all are same. X is equal to KT or K is equal to X by T. X means R naught minus R. What is X? Amount of reactant converted to product by time T. What will be that? R naught minus R. What is R naught? Initial quantity. What is R? Quantity available at the time T. Right? That's all about the integrated equation of zero order reaction. What about first order reaction? Integrated equation for first order kinetics. Next. First order reaction n equal to 1, where you are able to understand R is equal to dx by dt equal to k into R raised to n, and that is equal to k into R raised to 1, since we are dealing with the first order kinetics. Okay. Now this even you are able to write k into R naught minus x, because what is R? What is R? R is quantity available now at the time T. That will be initial quantity minus converted quantity. Many times you can find for exams initial quantity also written as small a. So it is small a minus R naught can be written as a, small a. Many questions we find such a terminology also. But in NCERT we are using R naught term, or sometimes they may use A naught. Depends. So this you can write it as K into A minus X. So it is dx by dt is equal to K into A minus X. That is R naught minus X. That is R. Okay. Now rearrange. It is dx by A minus X equal to K dt. Now integrating on both sides. Integral dx by A minus X equal to K integral dt. And the result will be minus log A minus X equal to KT plus C. That will be the equation. Integration result of dx by A minus X will be minus log A minus X and K dt, as all of you know. Now, to find out the quantity, integration constant C, you can apply time t equal to 0. At a time t equal to 0, x equal to 0. So what do you get? This is 0, this is 0. So you get minus log A. You get minus log A equal to the integration constant C. Isn't it? At the time t equal to 0. At the time t equal to 0, this will be 0 and this equal to 0. You get C equal to minus log A. And this value of C you can substitute here to get minus log A minus X equal to KT minus log A. Upon rearranging, you get KT is equal to log A minus log A minus X. And that is equal to KT is equal to log A by A minus X. And that is the integrated equation for first order kinetics. KT is equal to log A by A minus X. Right? Or it may be written, written in the regular terms as is used in the NCERT. You can write KT is equal to log R naught by R. Log R naught by R. What is R naught? Initial quantity. R naught is initial quantity. What is A minus X? A minus X is equal to quantity available now, R. So KT equal to log R naught by R. Or it is KT is equal to 2.303 log log to base 10 R naught by R. Like this. and that also can be used for plotting the graph. Suppose you are plotting the graph ln r naught by r versus time. You will get a straight line like this. Slope of the line will be kt. I mean k. Slope of the line will be k. This taken along the y-axis and time taken along the x-axis, right? Or in this case, if you are taking log r naught by r versus t, you will get a straight line like this, and the slope will be k by 2.303. This will come to left hand side. K by 2.303 will be the slope, right? Or the graph may be represented in a slightly different way also. You can write this format. You can write this format in a slightly different way. You see that log r naught minus log r is equal to kt. Upon rearranging, you get log r is equal to kt. Log r is equal to log r is equal to log r naught minus kt. I think it is clear. Log r is equal, rearranging the formula, log r is equal to log r naught minus kt. Now plot the graph, taking log r along the y-axis and time along the x-axis. You will get a straight line like this. You will get a straight line like this, and the slope of the line will be once again minus k, and the y-intercept will be log r naught, right? Same thing you try to do here. Same thing you can try to do there. It will be log r is equal to log r naught minus kt by 2.303, where the plot drawn will be log r versus time. You get a straight line like this, where the slope of the line will be minus k by 2.303 and y-intercept will be log r naught, right? The application of different format, in different form. You may be encountering questions based on graphical or formula based questions. So that is the integrated equations for first order kinetics. You can try k is equal to 2.303 by t log r naught by r. This is a typical format of integrated equation for first order kinetics. K is equal to 2.303 by t log r naught by r, like that. Is it clear? That is integrated format for first order, zero order reaction. Okay. Now another important terminology is half-life. A talk on half-life. All of you know what is meant by half-life. Half-life T half, or we call it as T 50%. T 50%, T half. It is the time taken for 50% reaction to get completed. Time taken for 50% reaction to get completed. Suppose we are dealing with a zero order reaction, n equal to 0. We know time t is equal to x by k. Already we have learned x is equal to kt, or time t is equal to x by k. What happens if it is time t half? Time t half. At the time t half, I hope you understand x is equal to r naught by 2. Because at the time t half, what is t half? Time taken for 50% to convert. So it will be r naught by 2. Initial quantity r naught, 50% converted means x will be r naught by 2. Right? So it will be t half is equal to x by k becomes r naught by 2 by k. That is t half is equal to r naught by 2k. Or rather you can understand t half is directly proportional to initial concentration. For a zero order kinetics, T half is directly proportional to initial concentration. So the graph will be T half versus initial concentration will be a straight line like this. And slope of the line will be T half is equal to R naught by 2K. The slope of the line will be 1 by 2K. Slope will be 1 by 2K. Slope of the graph for a zero order kinetics. Remember, not only T half, time for any percentage can be calculated. Time for any percentage can be calculated. You see here, now T half, that is T 50%. T 50% you are getting R naught by 2K, that is 0.5 R naught by K. What will be time for 25%? What will be time for 25%? What will be time for 75%? What will be time for 90%? What will be time for X%? See, 50%, 0.5 R naught by K, 25%, it will be 0.25 R naught by K, 75%, 0.75 R naught by K, 90%, 0.9 R naught by K, X%, it is X divided by 100 R naught by K. X% will be X divided by 100. You see 90 by 100, 0.9. 90 by 100, 0.9. So it is X%, X by 100 R naught by K. For any percentage time we can calculate. And it's quite interesting. Any percentage, it is directly proportional to R naught. Time for any percentage, it is directly proportional to initial quantity for a zero order kinetics. Clear? Right. So you must try all possibilities. You must try all possibilities. Next is about first order kinetics. What about a first order kinetics? T half for a first order reaction. T half for a first order reaction. How it comes? We know time T is equal to 2.303 by K log R naught by R. Isn't it? Now, what happens at a time T half? What happens at a time T half? It will be 2.303 by K log R naught divided by, what is R? At T half, R will be R naught by 2. At T half, R will be R naught by 2. How is that? T half means time for 50% conversion. So, at T half, 50% of R converted to product. How much is remaining? The other 50%. 50% gone. How much remaining? The remaining 50%. That means what is remaining R? It will be R naught by 2. So R naught by 2 converted to product. Remaining will be R naught by 2. Clear? So R will be R naught by 2 and you get T half is equal to 2.303 by K log R naught cancels log 2. It will be log 2 and that is equal to 2.303 by K into log 2 means 0.3010 and you are getting T half, the very popular relation, 0.693 by K. 0.693 by K. It also reveals an important point that T half is a constant. For a first order kinetics, T half is a constant. For a first order reaction, T half is constant. So how is going to be the graph? The graph for T half versus initial quantity, it will be a constant diagram for parallel to the x-axis for first order reaction. Right? Now, similarly, you can find any percentage. What will be T 75%? What will be T 75%? How is going to be? It is equal to 2.303 by K log initial quantity 100, remaining quantity 25. 100, let the initial quantity be 100. How much remains? 75% converted. What is remaining? 25. So how much you get? It is 2.303 by k log 4. Log 4. That is 2.303 by k log 2 square. That is 2.303 by k 2 log 2. You can easily understand it is 2 times t half, isn't it? T 75% will be 2 times T 50%. What was T 50%? T 50% was 2.303 by k log 2. What about T 75%? 2.303 by k log 2 into 2. So it is 2 times T half. Hope you understand. Okay. So T 75% will be 2 times T half. T half is a constant. Not only T half, T for any percentage is constant. What does that mean? Time for any percentage is constant. What does that mean? That means 100 becomes 50. 100 becomes 50. Suppose T half is 1 hour. 50 becoming 25, T half will be 1 hour. 25 becoming 12.5, T half will be 1 hour. T half is fixed. T half is fixed. So this is T half. This is also T half. 100 to 50 T half. 50 to 25 T half. Now 100 to 25. This is T 75%. It is 2 T half. I hope it is getting a picture. This is T 75%. That means 75% converted, remaining 25%. So time for 75% will be 2 times T half. Like that you can find out. And see, the reaction going like that will never come to an end theoretically. Nuclear reactions theoretically never ends. That is the meaning. Practically, of course, there is an end. Because you can't find out T 100%. What will be T 100%? What will be T 100%? It is 2.303 by k log R0 by R becomes 0. You cannot find. R becomes 0. R means quantity available now. It is 0 because T 100% we are talking about. It's not possible for a first order kinetics. You can find T 100% for zero order kinetics. What is T 100%? What is T 100%? It will be Tx% x by 100 R0 by k. So it is 100 by 100 R0 by k. It will be R0 by k. This is T 100% for zero order reaction, R0 by k. But that you can't define for first order kinetics. It is theoretically never ending process. So you have to practice doing T 25%, T 10%, T 99%, T 80%, T 99.99%, T 9%, 99.99%. Everything you must try practicing and also try to get a interrelationships. For example, T 99.9%. How do you evaluate? It is 2.303 by k log 100 initial quantity divided by 0.1, isn't it? Because 99.9, time for 99.9 completion. So 99.9 is completed, remaining is 0.1. Remaining is 0.1. So R0 I am giving 100, R will be 0.1. So how much you get? That is equal to 2.303 by k log 1000. Log 1000. That is 2.303 by k into 3. Log 1000 is 3. Now you are able to understand it is 10 times T half. T 99.9% will be 10 times T half. How do you understand 10 times T half? This is 0.3 into 0.3. That is into 3. You please compare T half and T 99.9%. T half it is 2.303 by K into 3. While T 99.9%, it is 2.303 by K into 3. That means it is 10 times. I hope you get the point. So try to evaluate time percentage for all and try to get the interrelationships. Right? So in general, we can have a idea. In general, we can have a idea. You can note it down. T half in general. T half is proportional to 1 by A raised to n minus 1, where A is the initial quantity, n is order of the reaction. Suppose it is zero order reaction. Suppose it is n equal to 0. You are getting T half proportional to A. A raised to 0 minus 1. 1 by A raised to minus 1 goes to A. Suppose it is first order kinetics. A raised to 1 minus 1, 0. That is T half is constant. Suppose it is second order reaction. 1 by A raised to 2 minus 1. So it is 1 by A. So T half proportional to 1 by A. Inversely related. What about third order reaction? 3 minus 1. So it will be T half proportional to 1 by A square. It goes like that. Hope the picture is clear. Right? Now, one important last topic from the chapter is temperature dependence of rate of reaction. Temperature dependence of rate of reaction. A very important topic. Temperature dependence of rate of reaction. It was studied and explained by Arrhenius, and he has forwarded an empirical formula, Arrhenius concept, Arrhenius formula. He is commenting K is equal to A e raised to minus EA by RT. This is an empirical relation. Arrhenius formula, Arrhenius equation. This is called a Arrhenius equation. Arrhenius equation. An empirical relation given by Arrhenius, relation for K versus temperature. K versus temperature. And the comment is that the relation of influence of temperature over the rate of the reaction is exponential rate. Exponential rate. A rise in temperature causes the rise in temperature causes the rate of the reaction to be exponentially increased. A normal reaction becomes explosively violent when the temperature is raised. Right? And there is the terminology temperature coefficient. Temperature coefficient. Temperature coefficient means K T degree plus 10 divided by K T degree Celsius. This is temperature coefficient. For example, K 35 degrees Celsius by K 25 degrees Celsius. The ratio between K value at a difference of 10 degrees is called a temperature coefficient. The ratio between K value, I don't have to tell you, K is directly relating with the temperature. R is equal to K concentration raised to N. When K changes, rate of reaction changes. Okay, so K, ratio of K at a two different temperature differ by 10 degrees Celsius is called a temperature coefficient. Usually the value comes in between 2 to 3. Usually the value comes in between 2 to 3. For example, K2 by K1 equal to 2 means temperature coefficient is 2. That means K2 is equal to 2 times K1. When you raise the temperature by 10 degree, K value becomes double. K value becomes double naturally means the rate becomes double. So for 10 degree rise, rate becomes 2 times. What happened to the rate of the reaction? Suppose the temperature is raised by 100 degree. Suppose for a reaction, temperature coefficient is 2. What will be the new rate of the reaction compared to old rate when the temperature raised by 100 degree? It will be a quite surprising data. For each 10 degree, it is doubling. Each 10 degrees it is doubling. Suppose you are raising the temperature by 100 degrees Celsius, the influence on the rate of the reaction will be, it is 2 raised to 10. That is 1024 times. The rate of the reaction increases more than 1000 times compared to the older reaction. That is the comment I made earlier. A normal slow reaction becomes explosively violent when the temperature is raised. Hope you get the point. That is explained empirically with the relation Arrhenius equation. K is equal to A e raised to minus EA by RT. A is called Arrhenius factor. A is called Arrhenius factor. That is also known as frequency factor. Arrhenius factor, frequency factor, collision factor, Arrhenius factor, frequency factor, collision factor. It is defined as the number of binary molecular collisions. It is the number of binary effective molecular collisions per second per liter. In unit time, in unit volume, how many effective collisions are taking place? That is called A, Arrhenius factor. And they are actually talking about a term effective collision. Effective collision. What is meant by effective collision? It is according to collision theory. It is according to collision theory. Collision theory is talking about effective collision. What is meant by effective collision? Effective collision means those collisions lead to result. Those molecular collisions leading to result, giving product, that is called effective collision. For effective collision, two things are taken care of, or two things are essentially required. The two things are, number one, there should be proper energy. There should be proper energy. The molecules should be sufficiently activated, and that is called activation energy, EA, activation energy. All of you know. The molecules should be, the colliding molecules should be sufficiently activated. They should have sufficient energy. There should be proper energy. Right? Number two, they should have proper orientation. They should have proper orientation. So proper orientation and proper energy can lead to make a effective molecular collision. You see 3-4 types of molecular collision. Case 1, a molecule moving like this, another molecule moving like this, they are moving slowly. Doesn't give a result because they simply collide and bounce back. Nothing happens because the molecule has no energy, proper energy. Okay, imagine second case, a molecule moving like this, a molecule moving like this, very fast, but no result, because they simply collide over here and they simply bounce back. As they were coming like this and bounce back, nothing happens. They had energy, they were coming very fast. They had high energy, but no use because they were coming like this and colliding. No proper orientation. This is no result due to lack of energy. This is no result due to lack of energy. This is no result due to lack of orientation. Now see third one. You see third one, a molecule moving like this, a molecule moving like this very slowly. Again no result. Here lack of energy. Here lack of orientation. Here lack of both. No energy, no orientation. The molecules were very slowly coming and bouncing. Nothing happens. Now only one case you get a result. What is that one case where you get a result? According to collision theory, the result is given by a fourth type of collision. A molecule moving like this, a molecule moving like this very fast. Suppose two molecules are moving very fast and they are coming head to head. There will be an effective collision and the bonds will be broken, new bonds will be formed and it will be converted to product. This is called the effective molecular collision, for which two things should be taken care of. proper energy and proper orientation. The molecules must be properly activated. Hope you get the point. And that is what actually we are seeing in the energy profile diagram. Energy versus reaction progress. For a exothermic reaction, this is reactant, this is product. You see, this is the energy of the reactant molecules. Actually, it has to cross this energy barrier. This is the threshold energy. It has to cross that energy barrier, for which it need to get this much of energy. And that energy we call it as activation energy. And that is what represented here, activation energy. The extra energy we need to supply. The extra energy we need to supply to the reactant molecules so that it can cross the energy barrier. So without that energy, they cannot complete the reaction, they cannot give a result. Right? If you take energy profile diagram, Maxwell distribution diagram, this is fraction of molecules along the y-axis, fraction of molecules along the y-axis, and energy along the x-axis. Hope you know the Maxwell distribution diagram. It's coming like this. And imagine, this is the energy limit. Just imagine, this is the energy limit, that is so-called activation energy. You can see there are molecules, but only these molecules will give a result, because these molecules are having a lower energy. They cannot give you a result. Only this much shaded molecules can give you result, because only they have energy more than activation energy. Hope you get the point. This is at a particular temperature T1. Suppose we are increasing the temperature T1 to T2. Suppose we are increasing the temperature, the new graph will be at a new temperature. The new graph will be like this. This is temperature T2. The graph gets broadened. The peak will come down and it becomes broadened, where you can see more molecules are getting activated. So the number of activated molecules, the fraction of activated molecules increases. That's why the rate of reaction increases upon increasing the temperature. Hope you get the point. All these are described by the empirical relation, Arrhenius equation. K equal to A e raised to minus EA by RT. A means Arrhenius factor, and this is called the energy factor. This is called the energy factor or Boltzmann factor. Energy factor or Boltzmann factor. E exponential factor. It is also called exponential factor. This is known as pre-exponential factor. A is called a Arrhenius factor, frequency factor, collision frequency, pre-exponential factor. And this is called exponential factor, right? That is Arrhenius equation. And it is K equal to A e raised to minus EA by RT. EA means activation energy. R you know, and T is temperature in Kelvin scale. Now take log on both sides. Take log on both sides, you get log K is equal to log A minus EA by 2.303 RT. That is in terms of common log or natural log. Ln K is equal to ln A minus EA by RT. That is the log format of Arrhenius equation. Log format of Arrhenius equation. When you plot the graph taking this formula, when you plot the graph, how do you get? Take log K versus 1 by T. It will be a straight line like this. Slope will be a negative slope, minus EA by 2.303 R. Slope is equal to minus EA by 2.303 R. And what is y-intercept? Y-intercept will be log A. Or even this can be taken for the graphical representation. Ln K versus 1 by T. It will be a straight line like this, and the slope will be minus EA by R, and the y-intercept will be ln A. So slope of the graph will give you an idea regarding activation energy. Greater the slope of the reaction, greater will be the activation energy. And what will be the nature of rate of reaction versus activation energy? Which is a faster reaction, the one with a lower activation energy or higher activation energy? Exactly. The one with a lower activation energy will be of greater fast reaction. Because lower the activation energy, the rate of reaction will be high. Because it has to cross that barrier, no? When this value is high, it is not easy to cross the barrier. The barrier is increasing. So lower activation energy means we have a fastest reaction. That is what happening in catalytic action. When you take uncatalyzed and catalyzed reaction, this is an uncatalyzed reaction, reactant converted to product. And this is the same reaction which is catalyzed reaction. This is catalyzed reaction. And the other one is uncatalyzed reaction. This is uncatalyzed reaction. No doubt this will be of greater speed. We all know catalyst is helping to increase the rate of the reaction. How is able to increase the rate of the reaction? It is actually changing the mechanism. When we use a catalyst, the reaction mechanism changes. So what happens? Due to which the activation energy drops. When the activation energy drops, means the route of the reaction has changed. The reaction has been taken in a different route of lower activation energy. When the activation energy is low, the rate of the reaction is high. Hope it is clear. Right? Now this the same equation may be utilized for two different temperatures. For two different temperatures, same formula may be utilized. You see this? Log K1 is equal to log A minus EA by 2.303 RT1, equation 1. Log K2 is equal to log A minus EA by 2.303 RT2, equation 2. So when the temperature changes, T1 to T2, K will change. Now just imagine you are doing equation 2 minus equation 1. Equation 2 minus 1. Log K2 minus log K1. You will get log K2 by K1. At a 10-degree difference, this will be temperature coefficient. Earlier we were talking about. And that is equal to log A will cancel. You get EA by 2.303 R taken out. EA by 2.303 R taken out. You get 1 by T1 minus 1 by T2. T2 minus T1 divided by T1 T2. This is another format of Arrhenius equation. So this is the one quite frequently being used in problems. Two different temperatures given. You are asked to identify the K ratio giving activation energy, or K ratio given at two different temperatures. You are asked to identify the activation energy. Like that, numericals can be coming. Right? These are the applications of Arrhenius equation. Right? Suppose you are encountering a problem like this. Suppose you are encountering a problem like this. Log K versus 1 by T for 2-3 different reactions. A reaction like this, a reaction like this, number 1, a reaction like this, number 2, a reaction like this, number 3, and a reaction like this, number 4. 4 different reactions, log K versus 1 by T graph are given, asking you which is the fastest reaction. Asking you which is the fastest reaction or which is the slowest reaction. So which is the slowest reaction, which is the fastest reaction? Slowest reaction means the one having high activation energy. The one having high activation energy means the one having high slope. The one having high slope, that is 2 having high activation energy. Therefore, the rate of the reaction will be minimum for 2. And which one next? The next slope is 4. The next slope is 3. The next slope is 1. So this will be the order of rate of reaction. This is the order of rate of reaction because this is the order of activation energy of reaction. This is the order of activation energy. Activation energy greater for 2, rate will be lower for 2. Activation energy lower for 1, rate will be greater for. Activation energy and rate will be inversely related. Greater the activation energy, slower the reaction. Right? This is Arrhenius equation and this is temperature dependence of rate of reaction. One of the most important topic with which that chapter is getting concluded, and where one of the most important theory also we are reviewing, it is collision theory. So let me conclude the chapter. We started from rate of reaction, average rate, instantaneous rate, differential form of rate of reaction, rate equation, order, molecularity, characteristics of order, unit of K, pseudo kinetics, determination of kinetics, graphical method, initial rate method, integrated equations, half-life, not only half-life, time for any percentage, zero order, first order, and various graphical representation, right? And finally, the temperature influence of rate of reaction, the very popular Arrhenius equation and the related aspects, including collision theory. Okay, we will meet in another class with another chapter. Till then, bye, see you, take care.